So we're looking at the reactor energy balance now, and we had made the point earlier that our reactors are almost like heat exchangers. So important is the role of temperature and energy in predicting the performance of these reactors. So we know we've got this highly sensitive reaction rate, so we want to carefully account for the energy that's changing across the system, because any small changes in energy may influence the temperature in the reactor and hence influence the reaction rate. So let's carefully develop that energy balance. And we start off first here with the comment on the influence of temperature. And we know that the reaction rate, most of the expressions are some kinetic rate constant multiplied with some function of the concentrations in that reactor. And so depending on the kinetics and on the order of reaction and so on, there's some function there. But the important bit to talk about first is this kinetic rate constant. And so up to now, we've just been treating the temperature as if it's one single value. However, when we unpack this kinetic rate constant, and we usually accept that this follows the Arrhenius relationship with temperature. So if you expand your kinetic rate constant, it has that form. Of course, that's not the most general form. In terms of the standard form, K equals AE to the minus E over RT. So what's shown here is if you have K referred to some temperature. So if you have K at a specific temperature value, then you can also write your K value in terms of an expression like that. So in whatever form you choose to represent it, you'll get an expression for K. And when you look at an expression like this, you find an extreme sensitivity to temperature. So these values of E are typically on the order maybe 50,000 joules per mole per Kelvin. It can be sometimes in the hundreds of thousands. And if you plug some typical numbers in 400 or 500 Kelvin here for temperature, you'll find an extreme sensitivity of K with respect to T. And in fact, there was that kind of, not a rule of thumb even, but there was a kind of general comment made that it's quite often the case that chemists will say that the temperature approximately doubles for every 10-degree change in temperature. So whether you're talking about Kelvin or degrees Celsius, for just a 10-degree change in temperature, you'll often find that the kinetic rate constant will double. So the numbers are such that that happens. So that just tells you how sensitive our system is going to be to temperature. And you might say, well, that only refers to K, but yes, K directly influences the reaction rate. And hopefully by now, from the previous sections, you'll have appreciated that our balances, our reactor designs are strongly influenced by the reaction rate. So this is really the driver behind our designs, the reaction rate that we achieve. This is, if you like, also something that nature is dictating. And so we are not free to pick these activation energies. Nature decides the energy required to undertake any chemical rearrangement. So we can't really do anything about this. I mean, of course, we can design our reactor space for a given temperature, so we can control the temperature in the reactor, but we can't change this relationship. We can't change that the system is going to respond so rapidly to a change in temperature. Yes, we can use catalysts and things like that, but typically there we are trying to improve the reaction rate response to temperature. We don't typically try to reduce it. So nobody's going to try and get a lower responsiveness of rate to temperature. So anyway, the point is the whole design is a strong function of temperature. And so it's really important for us, of course, to get a strong handle on the temperature. And then, of course, the way to do that is through an energy balance. So this section is all about developing an energy balance and doing it in the right way. And in fact, in the next session, we'll look at how to navigate the plane and actually get around some of the limitations that we'll find. There's another small note here that sometimes your temperature also affects your concentration. So if it's a gas phase reactor and if the pressure is low enough, then PV equals nRT, the ideal gas law applies. And you can rearrange this quite easily. So N over V is the concentration, which means concentration equals P over RT. So clearly here you can see as you change the temperature, concentration will change. So that will change this part of your expression, your rate expression. So that's true. Sometimes you actually have a temperature influence on your concentration. But even if you don't, really here, this Arrhenius relationship, this is so strong that this alone justifies treating your temperature and your energy balance very carefully. Okay, so that's the motivation for what we're talking about now. And then in developing that energy balance, if you think about what we did on the mass balance side, right? For the mass balance, we said rate of change of moles is molar flow in minus molar flow out plus the reaction rate. And it seems almost automatically or automatic to us that yes, we go ahead and do the same thing. Rate of change of energy is energy flow in minus energy flow out plus the heat of reaction. So we are familiar with this concept of heat of reaction. So it seems to us like, well, we just multiply heat of reaction by the actual reaction rate, and that gives us, all of this gives us the overall change in energy. And actually this is wrong, right? It's not correct to write something like this. And that's because, you see, this energy that's given off due to reaction is already accounted for in here. So in terms of inlet flow and outlet flow, these are already counting the energy. These terms are already counting the energy change across the system. And in fact, the energy difference across the system can be thought of as being the reaction heat. So in a sense, we are double accounting if we are thinking like this. And maybe to further try and unpack that, you see, when we say that when we say that we have a flow into our system, right? In a mass balance, we would just say the material flow in, the molar flow or the molar rate of change is simply equal to the flow in minus the flow out. In the case of the energy balance, we have to multiply by the enthalpy, so that will give us, this is, if you like, the energy that's coming into the reactor. So all our streams have a certain kind of energetic content, right? If the temperature is above 0 Kelvin, so if you think of 0 Kelvin as the zero energy state, right? The moment you go above 0 Kelvin, the moment, let's say, your inlet stream is ambient temperature, like 25 degrees Celsius, something like that, then this has an energy content. Of course, if it's 0 degrees Celsius, right, standard temperature, then it's still not what we think of as zero energy, because it's above 0 Kelvin, right? 0 degrees Celsius is still 273.15 Kelvin. So most of the time, that is an energy flowing into the system, even if we think this temperature is lower than everything than the temperature in the reactor. Still, that's energy that's flowing into the reactor. If you like, you can think of it as an energy momentum that's pushing into the reaction space. And in a similar way, when we have a flow coming out of the reactor, then there's a loss of energy to the space as well. So that's the flow of energy into and out of the space. And then we are starting to say yes, and that fully accounts for the reaction heat as well. So we're trying to unpack that here. So we're saying yes, there's a certain kind of quantity of energy flowing in and out, and our contention might be, well, doesn't the reaction break and remake bonds? So of course there's a certain amount of energy. So in the molecules you've got bonds. All the atoms have been bonded together in this molecular structure. So we know in the reaction bonds are going to be broken and bonds will reform, and the number of bonds broken won't always equal the number of bonds that reform. So it looks to us like the reaction itself is going to change the energy content. And that may be true, However, you see, you've already accounted for that. So when you look at what's leaving the reaction space, you do have a different number of moles flowing through there. So if you've gone, let's say the product has a higher energy than the reactant, then you will find a higher molar flow rate of the product out here. And then when you multiply by its enthalpy, that will tell you what this new energy is that's leaving the space. So that's my attempt to explain why just these two terms fully account for all the energy change in that reactor space. And you might say, but then why did we have a reaction term in our material balance? So you are claiming now, you meaning me, so I'm claiming now we are not supposed to have a reaction term here. And yet, if you go back and look at your material balance, you'll see, yes, you do have a reactor term. So why is that the case? And that's because when we wrote this balance, we wrote it on a specific component, component I, if you like. So we had flow in and flow out, and we had a reaction term. And so because this balance is so specific, because it's about a specific component I, it is necessary to account for the if you like, the creation of component I. So you possibly did not have I in, or you had a low amount of I in there, and then you may have had some other component J, which was translated and converted into component I. And so you can, when you are talking about individual species, you can talk about the creation of component I. However, you still cannot talk about the creation of mass, right? Mass and energy are not created or destroyed, right? And at least not in chemical reactors. So we are not creating mass. So if you weren't writing just in terms of component I, if you wrote instead in terms of total mass in the system, and then of course this is number of moles, so if we want total mass, then we have to multiply by the molar mass and add up over all species. So that's what I'm showing here. We multiply dni dt by mmi, the molar mass of component I, and add up over all components I. Then that's the rate of change, the total rate of change of mass in the system. And then we have to do that for each of our terms as well. So we multiply molar mass of I and add up over all the components in each of these terms. And well, that's just mechanical here. And then if you look at this specific term, we can of course write this slightly differently, because you'll recognize that the only I inside this integral is nu I. So we could remove this ratio as being the only part of this which is a function of I. And now, of course, these are stoichiometric constants. They are not varying with volume. So this is a constant of integration. So we can pull that out and we can rewrite it like so. Okay, so now we've got the sum mmi nu I over nu a. And we also said before that mass has to be conserved during the reaction. So the mass on the reactant side must equal the mass on the product side. And so if you look in the numerator here, this is indeed a product of the masses on the reactant side and the masses on the on the product side and the masses on the reactant side. So if you add all this, right, remember nu is positive for reactants and negative for products, then this is definitely going to be a zero. So yes, this term does become zero. So when you write a total mass balance, this term does zero out, leaving you with just that the total rate of change of mass is equal to the flow in minus the flow out. So total mass does agree with that. And then you might ask, well, but then why didn't we write for energy? Why didn't we write each component? And that's because we can't really separate an energy balance into specific components. We don't really talk about the temperature of the hydrogen in the gas or whatever it is. So in terms of us as human beings looking at the reactor, we can talk about a temperature. We don't talk about the temperature of that component in the gas. So we can talk about the temperature for phase. We can say the phase is this temperature, and it might even be different to the temperature in the liquid phase, even if they are in the same reactor. So, but that's not what we are saying here. So here we are talking about one phase. So there's one temperature. So we need to account for each component as parts of the fluid. So we don't tend to write individual species for the energy side of it. Of course, that doesn't prevent us from, if we wanted to, writing the individual contribution from a component. We can do that. And in fact, we have to do that for writing the energy balance, as we'll see just now. But in terms of writing the total energy balance in the standard way that we do it, we just don't default to writing individual species. And so that's why we didn't see that term at first there. So we are going to develop the energy balance on the understanding, we'll start it from first principles, and we'll see that this term pops out, and in a way that doesn't kind of violate and do something wrong like shown here. Okay, so we are going to develop this energy balance quite carefully and from first principles now. So the best way to do that is go back to our basic thermodynamics understanding, and of course we can say that the difference in energy, and by difference we are leaving difference in the abstract sense. So the difference might mean over time. What's the difference over time? It could also mean the difference across space. We could talk about the difference between of energy between one point and another point. So at this stage in thermodynamics, we don't try to be specific about what this delta refers to. We are just saying if you compare two things energetically, then the total difference in the energy across those two things will be equal to the amount of heat that was added, the amount of heat in terms of temperature, and the amount of work done. So when we use Q, the way I like to think of it is that's the heat added in terms of a temperature difference. So we apply some temperature difference, and then that's energy added or removed from the system. And then work done on the system. We pump it around, or we move it across two different elevations, or we do something mechanical. So this one is more mechanical, and then this one is more thermal. Okay, so that's your difference in energy. And then let's apply that kind of abstract view to this case where we've got some reaction space. We might even be doing some shaft work on the system. So we are applying some current, some external current, and that's driving this propeller. So that is an energy input that we have to account for. Then we've got flow in and flow out. And as we say, we can think of these as energy streams. We might also be adding heat or removing heat due to a temperature difference. So these are all the possible important players in terms of energy, in terms of the energy balance. So like we said, this is the kind of balance that we could apply. And so we are defining EI to be the energy of component I, and Fi to be the molar flow of component I. And so if you add up all the contributions from species I, then you can say the rate of change of energy in the system, that must be equal to the flow of energy into and out of that system. So you can say each component I in the inlet stream has a certain inherent amount of energy, and similarly each component I leaving the system will have a certain other inherent energy. And why are these not the same, right? If it's component I, shouldn't they have the same inherent energy? Well, you might have different temperatures, right? So your temperature here, maybe it's a cold stream coming in 100 degrees only, and then let's say the reaction itself was adding a lot of heat, and we were leaving at 200 degrees, then a component here will have a certain energy content which is not as much as the energy content leaving there. So just because the temperature difference, because the temperatures might not be the same in the inlet and exit, then the inherent energy of your species will be different as well. So anyway, that accounts for flow through. And then we may be adding heat in the terms, we may be adding energy in terms of temperature difference. So for example, if we have a heating coil here, so if you have a heating coil, you might be blasting steam into the coil. So the steam is in there and then the steam leaves. And remember, that's not a mass contribution. So we are not injecting steam directly into the reactor. So that steam is not mixing with the reacting mixture here. That steam is staying in the coil and exiting. However, across the walls of that coil, that temperature difference is causing thermal energy to be given into or removed from the reaction space. So we've got temperature difference energy going on here, and that's not the same as the reaction going on. So we can add heat that has absolutely nothing to do with the reaction and has nothing to do with the inherent energy flowing through here either. So that's there. And then we've got work done on the system. And here, again, we are adding mechanical energy to the system. So you've got out here a motor which is connected to a power source, and so that power is driving this turbine, and that's causing our fluid to be flung around faster. So that's a direct input of energy also. And again, that has nothing to do with the energy due to reaction here. It has nothing to do with the energy here or anything like that. So this is an additional source of energy into the system. So that's the work part of it. And in fact, this W is all mechanical energy that's done on the system. And this is specifically about shaft work. So this is, if you like, this is one of the specific aspects of work done on the system. You might be doing other work on the system. I mean, you might have a piston pushing down on this whole reactor, pressurizing it. So that would be other work done, and so on. So that's work done on the system. And then, as we said, the other forms of energy, just the flow. So the chemical, if you like, this is the chemical energy. So you've got chemical energy flowing into and out of the reactor. So no reaction terms as yet. This is just taking a straightforward view of the system. If you have a boundary here, what are all the energy contributions to that system? And those are all the energy contributions to that system. So that it looks like a nice strict energy balance. It's leaving very little room for doubt here. Here, just a comment. Yes, Q itself is in joules, and then Q dot. You are used to this notation by now. Q dot is a gradient in time. So if Q is in joules, then Q dot is joules per second. And we should always do that. We should always check here that our units agree. So this is joules per second. The power rating, remember this normally would be watts, right? So you have some motor rated in watts. And we know power is nothing but energy per time. So this is also joules per second. Then here, rate of change of energy with time. If this is energy, then this is joules, and then this is differentiated in time. So this is joules per second. So that also agrees. Then here, this is the inherent energy. And as we'll see, this is joules per mole. And so joules per mole multiplied with moles per second, that's going to give us joules per second. And the same here, joules per second. So everything here is joules per second. So if you like, the units agree. So that's always an important thing to check. We will expand on this just now and see exactly how we get joules per mole and all that. So anyway, that's the first form of this. And then in terms of this work done on the system, we can expand on this, and we can say that if there's a difference in molar flow, then there will be a difference, right? The pressure energy of the system. Remember when we talked about the volume expansion term, we said that the pressure difference was driving the flow, and we might get different flow rates through and so on. So yeah, you look at um, the kind of mechanical energy. So the flow itself through the system is also a mechanical energy done on the system. And here, if it's work done on the system, then coming in would be work, if you like, done by the system, and so on. So you account for the flow itself using these terms, and then you've got the shaft work here as well. So of course, if your volumetric flows are equal and so on, so most of the time we neglect this. We think of this as small in comparison with the shaft work term. So most of the time we neglect this term. But anyway, if you substitute, I shouldn't say neglect this term. This is important. We actually account for this by combining these terms, as we'll see now. So if you substitute for the work here, so remember it's this term. So if we just go ahead and substitute for W in here, then you replace that W by W sub S, W dot sub S, so that's there. And then you can group each of these terms with the other terms. So you've got F in and so on. So you can group your energy with your pressure volume, with your mechanical flow terms also. So you can group it like this, because we can see we've got the sum over Fi. So we can group it like this. And then we realize that, well, in terms of total energy, we can rewrite that in terms of internal energy. And that has more to do with chemical energy, chemical potential energy, if you like. So we can separate actual energy into internal energy, kinetic energy, and potential energy. So height difference energy, most of the time we think of that part that way, and then kinetic energy, of course. So if we apply that here, and then we look at this form, we usually ignore the last three terms, so we don't worry about this too much, and then we can rewrite energy as internal energy. So we can say EI is approximately UI. So then you've got U plus PV and U plus PV, and of course U plus PV is the enthalpy. So we've related now this mysterious E, this E that has a lot of stuff behind it. There are many possibilities behind this E. We've said we also need to account for mechanical energy here, and so if we add all that together, and if we ignore these types of energies, then we end up with enthalpy. And when you see a thing like this, hopefully by now you feel more at home. When you see a thing like this, you say, oh, this is getting closer to my chemical engineering expressions. I can see now an enthalpy, right? The moment you see enthalpy, you feel this kind of burst of happiness. Oh, I can get my heat capacity. I can go into a little textbook somewhere and look up the heat capacity of my components, and I can estimate enthalpy. I can go to enthalpy of formation and all that. So straight away, right, you see, oh, I don't have to worry about U or E. Now I've got H. I've got a nice enthalpy. I can work out numbers for these two terms. So this is starting to look easier straight away. These terms also you should feel much more at home with. Right, Q dot, you've perhaps spent a whole semester on heat transfer, and you have all these clever ways now of estimating the energy due to heat transfer. So you can say, whatever type of reactor this is, I can just go and look at the mechanism of heat transfer, and I've got my U, A, delta, T, and log mean temperature differences, all those nice things. So we can easily unpack for Q dot. And then shaft work. In fact, this is the easiest of all, right? The work done by an impeller on the system. Well, there'll be some motor out there, so you just go and peep at that motor. There'll be a nice little steel plate on there giving you the rating, or you can go and look at your bill for the month and say, oh, this fish tank is this pump in this fish tank is rated for, I don't know, 20 watts or whatever. So you can just look up the shaft work in watts, and then that gives you a number there. So for everything on the right hand side, we can easily identify a number, and so this is starting to look very easy to work with. Of course, we've got total energy on the system on this side, so let's see if we can improve on that. Well, in fact, it looks here like we are avoiding it for the time being. So we are saying here, just let's consider the steady state version of this equation. So if we do that, of course, then we have a 0 here. And let's imagine this reaction equation. So you've got two components, A and B, reacting to give us a different two components, C and D. And we have some unspecified stoichiometric coefficients, lowercase a, lowercase b, lowercase c, lowercase d. And then we are told there's also an inert I in the system. So it's a fairly general system, and you can easily imagine cases where if there was just one component, then you just set lowercase d to 0 and things like that. So anyway, it's fairly general. And so we can say, if we were to unpack just the first term, right? So going back here, if we just unpack the first term on the right-hand side, you can say the total enthalpy in the system is going to be the sum of each component. So you've got the four components. And so you may still have A and B flowing, this is at the inlet point. So at the inlet point, you can have A and B coming in. And then we know C and D are products, but let's include them anyway. If we have no product coming in, then we can just set zeros for the molar flow rates here. Of course, we might have product coming in. I mean, if we have a recycle and if there isn't perfect separation and so on, it can easily be the case that we also have product coming into the reactor. But anyway, that's there. And then we have the inert as well. So you've got some molar flow of inert and you've got some enthalpy of that inert. And so we have to include the inert. So even though the inert is doing nothing in terms of the reaction, it is still, the inerts are still carrying a certain amount of energy. So you've got some inert flow, so inert because it's not reacting, but it's still carrying energy in, and then we don't know how much inert is coming out. So F inert out might be different to F inert in. So that is another energy concern. So we have to include the flow of inerts when doing the energy balance, right? The inerts might influence us in terms of mechanical energy or thermal energy. Okay, where were we? Here, right? So your inlet stream of energy in terms of enthalpy is shown like that, and then it's quite the same thing at the exit point. Each of your species has a certain molar enthalpy, so joules per mole, and that molar enthalpy we can estimate, and we'll revise a little bit later how you estimate the enthalpy. And then the rest of this we've done in detail in your mole balances. We had defined the inlet molar flow ratio, capital theta, like so, and we had related that through that nice general expression. We said theta I minus nu I over nu A times XA times FA in. That was how you get the molar flow out. And we also include the inert here because we do need the molar flow of inert. So we can also refer the inert to the base component. So we can define a capital theta I for the inerts, and that product with the molar flow of A in is Fi out. Okay. And so if you put all those terms together, it looks like this. And note here that it's slightly different. We've grouped things slightly differently. So number one, we can rewrite this Fa out. And in fact, let's just do it quickly here. So we can write Fa out, Fa out. I'm just writing them together. Fa out is Fa in, and then times theta sub I minus mu sub I over nu sub A x sub a. Right, so that's our general expression, and now what we have is h sub a in f sub a in minus h sub a out f sub a out. And if we write those two together, we can replace the second term here. So FA out, we've said, equals this thing. So I'm just replacing here FA out with that. And then we can see we can group together the FA in terms. So let me just see how we did it here. Yeah, we grouped FA in, and we grouped out two specific parts. So FA in, HA out. So we can say F sub A in into, and then we've got here HA in, HA in minus H sub A out, and then here we have to multiply by this stuff as well. Anyway, right, so that's what we have here. If we write, if we try to group H A in, so you can see you can group it like this, and then this theta b. So what we did there was we further not subdivided, but we wrote it further like this. So we remove this theta I here, and then we kept this term as a separate one. So you can see there's another term here, minus FA in, HA out, nu I over nu A XA. So that minus multiplies with that minus, and you can say here plus F sub A in, and this is H sub A out, and in here is, well, it's just a factor, so I can say I should say nu sub I over nu sub A, nu sub A x sub A. Right, so here we've got this part, FA in times this difference, and then plus this extra term here. Noting that for component A, remember A is the reference component, so nu A, I should say here nu A, and these should be theta small I, theta small I, theta small I. And so here we can say theta sub A equals 1, and nu sub A, nu sub A over nu sub A equals 1. Right, this is obvious, but of course we have this term here, so and I was writing this generally as I. So we can see here we are going to get HA in minus HA out times 1. So that's what we have here. And then for the second part, we have FA in, HA out, and then times 1 times XA. So you can see here that contribution, okay? And I can see there's a minus sign missing here, or there's a minus out there. Okay, that's fine. Okay, so you can see for component A, that's what happens. We can see how we get the A part of this, and you can work carefully through each of the other species, and you'll see that they all have that form. Right. So you can see one part here where it's simply FA in multiplied with the difference in enthalpies and then times theta of whatever it is. So you could also just say, well, instead of theta b FA in, I could just call that FB in and then times that enthalpy difference. And then you have this extra term building up here. So for component A, simply FA in X. For the other terms, you can't say new A over new new I over new A equals 1. You can't say that for the other components, so you can't simplify these ones. Yeah. So when you look at this, you can see now we've managed to separate nicely the temperature difference part, right? So between inlet and exit, you've got a temperature difference here, and that shows up as an enthalpy difference. And then for the other part, you've got the reaction contribution here. So the FA in X part, this is all about the reaction. And it turns out that is it's showing up with these factors here. And in fact, that's our heat of reaction term, right? We look at all this and we can say, well, if I think about what this looks like, if it looks familiar, it looks like the heat of reaction that we've defined before. So the heat of reaction kind of pops out when you just compare these two terms in your energy balance. So that's again why I say that if you go and add a heat of reaction term to your energy balance, you are double accounting, right? The heat of reaction actually arises from the difference between the inlet and the exit flow. In fact, if you think about it, when we first wrote this part, right, we just wrote this down quickly because we knew we needed to expand for FA out. We wrote this part down and we know it's written in terms of the actual inlet flow of component A, and then there's another term that accounts for the change in A due to reaction. And so that's why we are seeing this new ratio and times XA. That is all ending up with this definition. So yes, heat of reaction is just a definition. It's only telling us about the energy difference that happened during reaction. If you like, it's the unaccounted for energy, right? When we look here, maybe when we go back to the diagram, here we have a temperature here and a different temperature here, so we can talk about an enthalpy difference here. But there is another difference which happens, which is the energy difference due to the reaction itself. So if we account for just the enthalpies, we'll only get so far. There's another part to this which pops out, and that pops out when you account for the contribution by reaction. So in your mole balance, you've accounted for the reaction part of it here. And you can see that is showing up as a separate heat of reaction term. So that is how the heat of reaction arises. That's how it's integrated already into our overall accounting. And by the way, you might be wondering, but I had HI in here and HI out there. Why is it that now you are saying, well, we've got the temperature difference? And that's because here, remember, we only grouped out for FA in. We didn't include FA out. So two things were changing here. The enthalpy is different and the molar flow is different, because your molar flow changes because species are disappearing and forming, and so those are different also. So if we go, another way to look at this is if you go and group out the temperature difference just in terms of the inlet flow. So if you ignore the fact that the number of moles are changing, and if you just look at the change due to temperature difference, you'll get a certain change, which is this part here, but then that won't take into account the reaction contribution. So the contribution of the reaction is to change the number of moles, right? The number of moles is different here and here. So and obviously that's the very basic thing. We are doing this because we want to change the number of moles. We want more product. So your number of moles changes, and that shows up here, and then associated with that change, you get an energy change as well. And in contrast to what we showed with molar mass earlier, this is not going to add up to zero. Right, your enthalpies of each of these species, there's no prescription that, oh, they all add up to the same thing or they all add up to zero. There will be some net heat, and it may well be the case that the energy state of the products is greater than the energy state of the reactants. And if that's the case, as the reaction goes, it's actually going to drop the temperature because more energy is going into maintaining the molecular structure of the product. So the energies here are different to the energies there. This whole thing is going to be a non-zero amount. This heat of reaction is, generally speaking, a non-zero amount. And so this is going to be a significant term. And of course, we didn't just write this out. This is something that arose from just accounting for the energy change through the space. Okay, so that's how your heat of reaction arises. And if you can understand this point carefully, then a lot of what follows just falls into place. Okay, so there's an example here. Well, this one doesn't as yet do anything on the energy side. It's very basic. So you've now specified numbers for those lowercase a, b, c, d, and we are given molar flow rates, and we just want to plot the number of mole or the molar exit flow rates, and we want to know what's the limiting reagent. So you've got A and B as reagents, and you can see here component, what's green? Green is B, so B runs out first, so B is the limiting one. Anyway, if you do that basic mole balance, you can draw something like this. So you can play around with this. Anyway, let's go on to just reminding ourselves how to calculate these HIs. So I said the moment you see capital HI, you feel a bit happier. So how do you actually do that? So to calculate enthalpy, normally we have the enthalpy tabulated at some reference temperature. So we are told, for hydrogen, the enthalpy at 25 degrees under this pressure is this value. So you have some reference amount, and then you'll say, yes, but I'm not at that reference temperature. I want my reactor to run at 200 degrees. So I need to add some other energy to get my actual enthalpy. And you typically estimate this amount beyond the reference value in this way. You typically have a heat capacity, and so you just integrate the heat capacity between the reference temperature and your temperature of interest. So you just integrate that, and that gives you that delta enthalpy, and then that's of course your enthalpy for that temperature T. And then of course that's true, but if you have phase changes in between, so let's say at the reference temperature it was a solid, so the reference temperature is low enough that you are actually in the solid state, and then let's say your temperature, your selected T value, was high enough that it was a liquid or even a gas, then there will be a stage where your solid starts to melt, and so there'll be an enthalpy change due to the melting heat, which can't be accounted for by a heat capacity style of a thing. So that's where you have to add in heats of melting. And then of course if you go all the way from a molten thing, from a liquid thing to a gas thing, then you also have to add in the heat of vaporization. So if you have so many phase changes, then instead of integrating all the way to T in one shot, then you have to integrate up to the melting temperature. So you estimate the enthalpy just for going from reference to melting temperature, and then you add in the melting temperature. So that would be tabulated as well. So you look that up and add that, and then you have to go from the melting temperature to the boiling temperature. So if your final temperature wasn't in the molten state, if it was beyond that, then you still have to integrate from melting to boiling. So you add in that part, and then at the boiling temperature, you still have to jump into the gas phase. So you need to add that discontinuous jump for vaporization, and then from that vaporization point to your current temperature, you integrate your heat capacity into that temperature. Right. So most of the time we don't. Well, I don't. Sometimes we don't have phase changes, and then it's as easy as just doing this. There are some times when you actually want to flash the reactor. So you might be feeding as a liquid, and then the liquid comes in and flashes. And that can actually be a strategy for reducing the temperature in the reactor. And in some polymerization reactors, we actually do that. So sometimes you end up having to do some of this. But in what we'll do in the rest of our developments is assume it's as simple as this. So if it's not as simple as this, then you just have to do some extra steps here. So conceptually, it's nothing that different. So anyway, that's the framework for estimating enthalpy of any component. And then this is just a comment that your heat capacity, quite often people think of it as a fixed value. However, heat capacity may well be a strong function of temperature. So whatever it is, we put the right function of temperature in here, and then we do that integration. So here we are not assuming it's constant. Quite often we are given this. Well, actually, sometimes I see B over T. So anyway, whatever form you have for heat capacity, you use it and you integrate it there. So that's just a refresher on enthalpy. Right, and here now we are just thinking, well, what if there isn't a phase change, and what if it is fairly easy? So then our heat out is going to be the reference temperature plus the reference temperature to our exit temperature, so that would be there, and then minus H in. And so the enthalpy at the inlet point will be the reference temperature up to the inlet temperature. And so we are looking at the difference between those two values. So you can see this reference temperature terms are going to cancel, right? There's a minus there. So you add those together, that vanishes. And then you are adding this integral reference temperature to out and then reference temperature to in. So if you combine those two, you can say that's the single integral T in to T out of our heat capacity. Okay, so that's a nice simplification that we can use. Right, so instead of having this big FA in HI in minus HI out, now we have this much friendlier heat capacity version. So again, this is looking much closer to the nice chemical engineering style of equation that we are familiar with. And then, we have this heat of reaction term here. And of course, we had said also that this is the net result of some enthalpy contributions. So let's go back and look at that. So our heat of reaction looks like this, and of course these are all enthalpies in here. So again, the heat of reaction has a temperature dependence. So we have to respect this temperature dependence. If it's significant. And so here, if we can work out the enthalpy at some reference temperature, then we can break this down. So delta heat of reaction, we can take each of the terms weighted by their stoichiometric coefficients. I'm just looking here. Yeah, I haven't written that out, but we can say the heat of reaction for all the species. So here we can say delta H super R, and this time at the reference condition. Now I don't want to use another capital R, so I'm just going to say sub 0 is equal to the heat, the enthalpy at the reference temperature. So we're going to say here sum over I of the enthalpy of component I at the reference temperature, so T ref, and weighted by nu I over nu A. Right, so that's the reference heat of reaction. That's how we calculate the reference heat of reaction. So for the given reaction, that dictates the stoichiometric coefficients. Then for the species, we just look up the reference enthalpy, and we can use that to estimate the standard, the reference heat of reaction. And then in a similar way, we can estimate the change from the reference value to the reacting temperature, the reaction temperature T. So this delta Cp, in a similar way, we define the stoichiometric ratios. So I'm just doing it here. C sub P for the reaction. So this is all specific to that reaction, because of course these stoichiometric coefficients are specific to the reaction that we are talking about. And then we just take the heat capacity of each of the species there. Right, so that's how you get these delta values. Okay, so so this is it's not really necessary to do this kind of expansion. It's just kind of nice to do, because we like to write a reference heat and a delta Cp style of an integral. So this is just, if you like, if we want to get this style of a thing that we are used to seeing for components, we can write a similar thing for the reaction itself. Okay, so that's how we can do these things in terms of the thermodynamics. And following the same example from earlier, we had ABCD and lowercase abcd, and we were given some amounts, some flow amounts. And now the question is saying, given the heat capacity, and here I think we are just saying assume that that this heat capacity is constant across temperature, and then given these heats of formation. So the reference temperature is 298, and we know the heat of formation for each of these species. Then we want to know how's the heat of reaction changing over that temperature range. So over about 50 Kelvin, we would like to know what's the heat of reaction. And so you can do the same calculation. So do this as an exercise, use the developments shown here, and then show that you get this heat of reaction. That's how it looks as temperature varies. Okay, so that's generally how we can estimate heat of reaction, and that's how we can develop our energy balance. So now we would like to apply all this in some reactors, and you have to admit, up to this point, we have made no prescription on the type of reactor. We didn't say this applies in a batch reactor or CSTR or anything like that. You could say, yeah, well, the way you drew it here, it looks like a CSTR, but we didn't need any assumption about perfect mixing. In a sense, what was happening here didn't matter at all to us. It turned out that the only thing we needed to know was the flow rate here and the flow rate there, and the temperature here and the temperature there. That's all we needed to develop the energy balance we showed. So the nature of the reactor, the nature of the mixing in the reactor, seems not to have influenced our energy balance. So that means that energy balance is true for all the types of reactors we've talked about, and possibly other reactor types as well. So let's see now how it's going to look for each of the specific reactor types. So here, that's the refresher. That's still there. Okay. So here we are looking now at in fact, we still aren't talking about CSTR or anything. Now we are just expanding on this term. So I guess we are just expanding on each of the terms in our general energy balance. And our heat added to the system due to temperature difference, so applied heat, nothing to do with the reaction itself. If we are applying some temperature difference to the reactor walls or sticking a little coil in and getting and forcing a temperature difference, then we can estimate that heat just from heat transfer considerations. So we estimate an overall heat transfer coefficient, and you do it in exactly the same way as we do in heat transfer. You look at internal temperature and across the wall, and the external temperature and the external heat transfer coefficient and the internal heat transfer coefficient. So all those nice things that you did in heat transfer, the exact same things apply here in terms of estimating the overall heat transfer coefficient. Just note a little bit of notation collision. We used U for internal energy earlier, so that's not the U here. This U obviously is the overall energy, the overall heat transfer coefficient. And then this is the heat transfer area. And again, be very careful with these things, right? The heat transfer area might not be the same as some other area. You could define the cross-sectional area through the reactor, and there it depends what section you are talking about. So there are many multiple definitions for area. When you meet catalysts later on, the area of the catalyst is another important area. So there are many areas you could define. So just make sure that when you are using this, that this is specifically the heat transfer area, right? And then there exists some temperature difference, right? That's why energy is being transferred in this way. There exists some temperature difference. And again, many temperatures apply in the reactor. You've got an inlet temperature, you have an exit temperature, you have a reactor temperature, you have a temperature in the heating coil or the cooling medium. So you have to be very careful in picking the right quantities here. So if we are talking about heat transfer due to temperature difference, you have to figure out which things are different, and then that will tell you which temperatures to use here. Right? We'll come back to this when we apply it. Now, the other point made here is it's just a reminder from heat transfer that we know we can write this kind of difference at a specific point. So at some point in space and at some instant in time, there exists some temperature difference, and then that leads to a certain heat transfer rate. Now, if instead of at a specific point, if we were looking at a difference that applies over an entire sub-volume, so for example, if you have a CSTR, then you can talk about a temperature difference across the whole CSTR at different points on that CSTR. And then you've seen before the notion of a log mean temperature difference. So there exist multiple points of temperature difference, and we can estimate the mean temperature difference. And you've seen this in some detail in heat transfer. You've looked at how to estimate the log mean temperature difference. And this wasn't an empirical thing by any means. This was something that was estimated carefully by doing a whole energy balance, and it popped out to be something like this. So going back and revising your heat transfer will stand you in good stead for this course. Okay, so let's now think about applying all this to a CSTR. Right, so you've got flow in here into the CSTR and flow out here. Flow out here. Right, and so be careful. This double line here is all about the reaction space, right? So you can see flow in this pipeline. It enters the CSTR space. There's no flow here. There's only flow out here, right? So in terms of your main reaction and your main species, you've got flow like this and flow like this, T in and T out. That's different to the flow here in this jacket. So if you can imagine, you've got this short, fat reactor, and then you build another tube that sits around that reactor and is enclosed at the bottom. And then maybe you force an oil or something like that through this jacket. So that oil is only going to flow here, and if you can imagine, it's flowing around the walls of the reactor. It can't flow up this way. It can only flow out here. So there's an oil out here which is exchanging heat across this reactor, but it's not exchanging mass. So that oil can't enter the reactor. It's just staying on the jacket side and it's leaving here. And so there's a heat transfer going on between this reactor and this jacket. And here you could imagine maybe 200 degrees coming in here, and then let's say this was heating. So maybe this is 400 degrees. So maybe oil goes in here at 400 degrees and leaves here at 300 degrees, right? Because it's giving up heat into the reactor. So 400 and 300. And then maybe we are coming in here at 100 degrees and leaving out here at 150 degrees. So maybe the temperature goes up here by 50 degrees and goes down here by 100 degrees. But at all points, the temperature difference stays within the driving force. So I'm just going to draw that quickly here. So let's say you've got let's say 2 points, and let's say your oil is heating us up. So the oil comes in at one temperature. So let's say this was 400 degrees here. 400, drawing with the mouse is not so easy. 400 and 300 here. 300, and then you've got your reactor, which came in at 100 and left at 150. And you can see these lines never cross. The reactor gets heated up by the oil and maybe by reaction itself, we're not sure. But anyway, the reactor is undergoing heating, so it's fed in at a low temperature, 100, and it leaves at 150. And then the oil enters the jacket at 400 and it leaves at 300. So during the time of exposure between the jacket and the reactor, the jacket is losing heat. So the oil is giving up its heat across the wall of the reactor, and that's helping to heat up the reaction content. So eventually the reaction content leaves at 150 and the oil leaves at 300. So there has been heat exchange across here. However, at all stages, you can see the jacket was always at a higher temperature than the reactor. So even though its temperature dropped, it never dropped so low that it was meeting the same temperature as the reactor. So it never got the chance to equilibrate in terms of temperature. So there was always heat transfer, although likely the heat transfer rate was lower towards the end than at the beginning. So that's what can happen in your heat transfer. And of course, the higher the rate of on the oil side, the lower the temperature drop will be. So if, let's say, this was done at a rate of 1 ton per second. So let's say you were pumping 1 ton per second and it went down from 400 to 300. Then if you pumped instead 3 tons per second, then it might do something like this. Yeah, let's try it a bit better. So maybe it went down to 370. So depending on the heat transfer characteristic as you change the flow rate. So if you apply a higher flow rate, then your temperature, of course you are still giving up heat, but because you are pumping at a higher flow rate, let's say 3 tons instead of 1 ton per hour or whatever it is, if you are pumping at a higher rate, so if you are pumping oil faster through here, then the oil would be at a higher temperature, and there would also be a higher rate of transfer. So around here you'll have a stronger difference. So your reactor will also increase in terms of the final temperature it goes to. So that might be, one, I don't know, let's make it a bit different, 160 or something like that. And another thing to note, here we said 400 versus 300, and then here it was 100 versus 50, so a 50-degree change here versus a 100-degree change there. And that can easily happen. The heat capacities are different, so the net or the average heat capacity of the stuff in the reactor, that heat capacity might be higher than the heat capacity of the oil, and so that's why even though it's an equal amount of energy transferred between the two, but the temperature difference won't be the same because the heat capacities are not the same. Okay, so anyway, that's what's going on in terms of the jacket and the reactor. And now we can make some definitions. So we've already defined T in and T in and T out over here. So that's defined for the reactor side. And then for the jacket now, we also have to define TA1 and TA2. So it's a bit of a strange choice, but anyway, we just need two more variables because we need to think about how we can account for the energy change on the jacket side as well. So anyway, that's what we chose, and then we can borrow that concept of log mean temperature difference. So that was the standard definition. You'll have seen this form of it. In the context of the reactor, if we choose A to be the jacket side, then it's TA1 and TA2. So that's the jacket. And then for the reactor itself, the B's, TB1 and TB2. Now you'll see we've just got T's here. And that's, so if we assume that fine, we are feeding at some temperature here, still the CSTR is perfectly mixed. So that means the temperatures are the same at all points in this reactor. And so even if you enter here at a temperature T in, which is different to the temperature here, in terms of what the jacket can see, the jacket is only in contact with the reactor itself. So the jacket is only seeing one perfectly mixed reactor, and everywhere in that reactor the temperature has this value T. So in terms of the temperature driving force, all the TBs can be replaced by T's. Okay, so that's how log mean temperature difference looks here. Another thing to note is we know this expression is precise in the case of a double pipe. So when you first derived this expression, it was for either counter or co-current flow in a double pipe, and this was exact. You derived this and you proved this was true. And this is not quite a double pipe because you've got, number one, you've got flow in this weird way here, coming in here and going out the side there, and then you've got flow in at one point and across the jacket and out at another point. So it's not quite the same as the double pipe flow. So here there's no flow straight through here. It's not like the flow is straight down here and then straight around there. It's a little bit different. But we are applying the same definition for log mean temperature difference. So this is again an engineering feature that even though we really should go and rederive this whole thing for this other weird flow pattern we've got going on, we don't do that. We just say, oh, close enough, let's try this out. And so we try this, and we actually find in most situations this is very close. There's hardly any difference, and even though the flow is not quite the same, and we just go ahead and accept it. And I'm being a little bit casual there. I'm being a bit critical of us as chemical engineers. And it's true, mathematicians will throw up their hands and say, this is terrible, you guys should pack it in. But in reality, one of the features of engineering, and I would say that this is, if you like, the formal thing that we as engineers do that makes us succeed, it's that we appreciate approximation science. So you see, if we had waited to derive the Navier-Stokes equations, and then if we waited for computers to be able to solve Navier-Stokes equations before we built the first reactor, right, nothing would ever get done. if you look at the Haber process, and Franz Haber did terrible things in his life in terms of chlorine and World War II, but also he produced fertilizer which revolutionized agriculture, and that's why we are able to live today. That's why we are at 7 billion people on the planet today. And you could say, well, there are problems with that, but setting that aside and looking at all the progress that we have made, all the reactors built, everything that we've done, all the contributions by chemical engineering to society, it's because we didn't sit and wait to solve this equation or that equation. We said, ah, this seems close enough. Let's try it out, and does it give us a good enough approximation? And you can formalize this. You can in mathematics there is you can define the sensitivity of an output variable to the inputs. So sometimes you find there are inputs that actually don't change the output that much, and then you just chop it out and you say, look, I don't care about that last 0.002%. So I'm just going to neglect those inputs, and that simplifies my whole development. And so I accept this approximation. It's good enough for me, and I'm going to design the reactor based on that. So that's, in a sense, what's happening here. We accept this as a reasonably good approximation for a CSTR, and so we can apply the log mean temperature difference. Right, and so you can rewrite it like this. So this is exactly the same thing, right? You've got minus t plus t here, so that's that, and then log of that difference. So that's how in the CSTR we can find an expression for q dot. Okay, so that's one. And then the other thing we could do is say, well, I have this expression for heat capacity. Yes, I'm supposed to use a quadratic and so on. So if I go and plot the quadratic over its whole lifespan, let's do a new, okay, let's just clear this. So if I go and I think about how my heat capacity is changing across the whole space, how my heat capacity is changing over all possible temperatures, and it's doing something like this. So if you are looking between 0 and maybe 1000 Kelvin, you can say, oh, clearly I need to use the whole temperature. But then if you look at it again and say, well, I'm only working over 300 and 350 degrees, which is here. So over this region, I can take a good enough approximation of heat capacity to be this number. So you just read the number off and you say, well, I'm just going to simplify my equation. I'm not going to bother integrating this thing. I can just take a single number here, and I can way simplify everything for myself. Okay, so that's how we also simplified this here. So that's another thing. Now, when you look at this, you say this is still fairly complicated. I've got 3 temperatures here. I've got my jacket temperature in, my jacket temperature out, and my reactor temperature. So this is still looking too complicated for me. And then you say to yourself, well, under what condition could I chuck out one of these variables? And you think, well, what if I used a nice high flow rate through my jacket here? Then my exit temperature will be closer and closer to my inlet temperature. And so instead of dealing with this 2 different temperatures, let's just call it 1 temperature. And you can go ahead and do measurements like that. You can go and stick in a little thermometer here and another one there and say, oh, the oil only changed by 2 degrees. And, I'm operating at 400 degrees. So that 2 degrees is making no difference to the life of this CSTR. So let's just say TA instead of TA1, TA2. So we go ahead and do that, and then we get a nice, really simple expression here. And then we say further, oh, exponential, that exponential makes the whole thing look unpleasant. Can I get away from this? And then if you look here, you've got UA MCP. Now you've said, well, I'm going to use a nice high flow rate so I can get similar temperatures, TA1 and TA2. So if this is nice and high, then this number here is going to be a nice small number. So if you're taking the exponential of a small number, let's think about the exponential function. Right, remember your exponential looks something like this. And the exponential function has the nice feature that it comes from the gradient being equal to the value, right? dy dt equals y, right? That's the definition behind the discovery of the exponential function. And of course, we can spend all day just mooning over the exponential function and the difference it's made to our lives. But for now, just noting dy dt equals y. And we are saying, especially at low values of t, the exponential is approximately equal to the value. So at low values of the exponential, let's write it here. So, oops. So we can say exp of x for x tending to 0, x of x okay, let's just do it here. Okay, so for small values of x, this is approximately x. So you can have a look here with the exponential function and use the fact, remember here that when x equals 0, x of 0 is 1. So the gradient here is 1. So as long as you stay at close values to 0, your gradient is 1, which means the derivative here, which is x of x itself, is equal to x. So you can show mathematically, so just quickly, you can just play around with this. So x of 0 equals 1, and so and also the fact that the x function comes from dy dt equals x of t. Right, so use these three together and you'll easily see that this is true. So as long as you stay close to the 0, your gradient is 1, which means your x is similar to y. So we can just we can say this thing, if we are using large flow rates here and this number is small, then this whole thing is approximately equal to this thing, right? And then you've got 1 minus that, and so it's as simple as ua of mj, and then that m dot j cpj can cancel with that one, leaving us just with this nice simple expression. Right, and you see it's really wonderfully simple now. You just need one value, and normally we'll just go and say, oh, just use that temperature there. And we know this reactor is running at 1 temperature T, it's trying to be perfectly mixed. So you just need one temperature difference here, and you do need an overall heat transfer coefficient. We at least have to do that much. And you just need the inside area of this wall, or the effective area across the thickness of the wall, if you want to be more precise. So anyway, for your CSTR, you can make the case that it's as easy as that. And of course, there are some things. Your flow rate has to be high enough and all of that. But anyway, your Q dot term can likely be unpacked in this way. So as engineers, those are the nice simplifications we can make, and that's how we can progress the field. We also typically find that the shaft work is relatively small in comparison with the other terms. So we typically neglect this, even though we can just read it off the motor. So that's not difficult to do. But anyway, we can write a balance like this. Quite often also, our heat of reaction, we know, strictly speaking, we need to expand that into a reference value and a difference value. But normally this term is much larger than this term. So we often just chop this term out as well. So if that is much greater than that, we can also approximately say this. Okay, and you see that generally applies. I know we got this for the CSTR case, but this was the only place, well, yeah, behind the T as well, but that was the only contribution, that was the only reason for saying CSTR. Quite a lot of this can be applied to other reactors as well. And so that's again, we can start to think as chemical engineers, we are allowed to make nice approximations, clever approximations. That's what I should say, to credit us and make us sound good. But we can do it like that. And so anyway, that's the CSTR. That's a very good approximation to the energy balance. It's giving us a nice relationship between the conversion we achieve and the temperature in the reactor. So that's the energy balance for the CSTR. In this example, we actually go ahead and estimate how good those approximations are. So sometimes you can go back and check the implication of making those approximations. And so here I'm plotting those equations at different stages of assumptions, and you can see they are fairly close. They are close enough that we would probably accept this for design purposes. If you try to exaggerate one of those, or you increase the jacket fluid flow rate, you show how much closer the lines get, and you can do things like that. Okay, so that's the CSTR. That's how you develop the energy balance there. Let's think now about the tubular reactor. So more like a PFR. So number one, we know the conversion changes down the PFR. Number two, if we have a jacket around this tubular reactor, then the temperature down the tube is also changing, and then the temperature in the heating or cooling jacket, that's also changing. And that's because there's constant heat transfer between the reactor contents, so across the wall, so between the jacket and the reactor content. Starting first with the adiabatic case. So adiabatic means no heat is added, so you don't apply any heating here. And in fact, it's not enough just to not flow something through here. You also have to say there's no heat loss to the environment. So perhaps this jacket is acting like an insulator, a heat insulator. So if you apply that and assume there's no heat loss, so that term knocks off. And then here also we don't have shaft work. We don't normally think about shaft work involved in a plug flow reactor. So those two terms can disappear, leaving us with just this stuff. And then you see the same form of equation for the CSTR. So if we go back here for the CSTR, we have those terms, and then we also have this extra stuff here. That's because of the jacket. In the case of the PFR, we are saying in the adiabatic case, when we don't add heat, then we can just neglect that part there. And so that's what we get. That's what we get here. Right, so that's how conversion varies with temperature down the PFR. Now, I would like to say here that this relationship is an important one, and it's also not specific to the PFR. You see, the only thing we did in this development is assume that these terms were zero. So we just assume there's no heat being added to the system or removed from the system, and we assume no shaft work. So if you chop those out, right, if you claim there's no heat added or no work done, then you are getting a relationship here which is relating the conversion to the temperature. And I'm claiming that this is important because it gives us a relationship that that in a sense always applies. It's almost like a nature relationship. So if your temperature is a certain number, so let's say we knew we were feeding at 200 Kelvin, and we saw at the exit we got 300 Kelvin coming out, and we stick those numbers in, 300 and 200. Then you see we can't do anything else here. We do choose our inlet flow ratios. That's fine. And then heat capacity, that's dictated. We can't change that. And then the heat of reaction also. These are all thermodynamic things. So it's telling us that there is a given conversion. If we have 200 coming out and we put 100 in, then that prescribes already what the possible conversion is. So maybe it's 60%. So it's saying that for that reactor, if you achieve this temperature difference, then you must have converted to this extent, 60%, I just said. So that is a relationship for the adiabatic case. It's telling us that for this set of species, for you to raise these species by this temperature, right, the only possible way you could have done that in the absence of other heat being added, the only way for you to raise these species, right, with these heat capacities and this heat of reaction, the only way you could have gone from 100 to 200 is if you had accomplished that conversion. So this is an important relationship. It helps us understand the relationship between temperature and the achieved conversion, right? So even if you have a reactor with lots of heat transfer going on, it's always useful to think about the adiabatic relationship, to simulate it, play around with temperatures, and see how the conversion responds. That gives you a good indication about the tendency of that reaction to respond to temperature. So I like to think of this as a general expression. Anyway, if that's true, if you aren't adding heat, if it's adiabatic, the other thing you can write is the mole balance. And again, the mole balances obviously still apply. Just because we've gone and done the energy balance now, it doesn't mean that the mole balance doesn't still apply. It does mean that we have to think about updating this in the light of temperature not being the same. So let's just rewrite this equation here. So we have here dx dv equals minus RA over FA in. And let's say this was for a second order reaction. Right, so then if it's a conversion of A, then this will be K times C sub A squared. And now you see your K there is a strong function of temperature. Let's say it's in the liquid phase, so we aren't worried about concentration changing with temperature. But you see now this reaction rate, it always was a strong function of temperature. And now we can see explicitly there is going to be an additional difficulty. Right, before we just fixed this as a constant number, but now we have to acknowledge that temperature is changing. And even if it's adiabatic, even if you are not adding heat in the jacket here, still your temperature is going to change down the tube. So because the reaction itself, if its heat of reaction is not zero, then on the balance your temperature is changing in that tube. And so you might enter at a high temperature here and it goes down, or the reverse, more likely, comes in cool and heats up as it reacts. So the temperature is changing down the tube. So that means we do need to revise this. And so we do need our Arrhenius expression. So we need to know K equals A e to the minus E over RT. So we need to know A and E, and then we need to know T. So as we integrate this, we need T as a function of V. So T is changing along the tube. And so as we look down this tube, temperature is changing down this tube. And now if it's an adiabatic case, we can just go ahead and use this nice equation. So adiabatic case, this equation applies, and that means we can just calculate, we can change this equation around and bring t across here and move x in there. So that means for the current value of x, there is a current temperature. So when you integrate this, you can just substitute, you can say here t of v is some other function of x, right? So you can use that adiabatic equation and say it's some f of x. And so you can go up here and say, well, even though I need t, I can just say t is a function of x, so I can just substitute here, it's k of f of x. So we still have to use this function, right? This k here, when I say it's k of f of x, it's this k of t equals this thing. So you have to stick in here the f of x value from here. So anyway, you can use the adiabat in that case, right? But of course, that's not always going to work. Sometimes you are going to try and control the temperature down the tube. You perhaps don't want this reaction running away, or you want to heat it up or whatever it is. So you want to control the temperature here in some way. Doesn't mean it will stay constant, but you like to try. So we have to think about a non-adiabatic version of that. So we'll talk about this energy balance now. Then just to point out here, there's another continuation of that same example. Here you are given tubular flow and the flow rate, and you are given enough detail. So here's your Arrhenius expression. Your A and E values are given to you, and you've got the same constants as before. You are told the total volume, and we want to know the overall conversion and temperature. So you can do this easily. And you can see here conversion rose and temperature was rising significantly. It's over 200 Kelvin change in temperature. Anyway, see that you can replicate this. Okay, so that's in the adiabatic case. Now, if we are adding heat to the system, then we have to say that at each stage, so at each stage along the tube, we are experiencing heat transfer. So let's say we pick a point here, then there does exist a temperature in this jacket, so TA at that position Z, and there does exist a temperature in the reactor. So the difference between those temperatures is going to cause a driving force, and heat is going to flow across the wall here. So we have to account for that, and so now, non-adiabatic case, we have to acknowledge Q dot is not zero, and so at some position there exists some temperature difference, and we here we just change the variable, but instead of integrating around the area of that heat transfer, we change it to the volume variable, because we are used to integrating down the volume of the tube. So anyway, we can just take out a factor of A. So if A is meters squared per volume, then we can change that to volume there. So you can do a small change of variables here. So yeah, you can calculate that value like this. All right. So for a cylindrical vessel, your specific surface area looks like this. So per reactor volume basis, right? So so we go back to the energy balance, and we say our Q dot now, right? And this is exactly the same as so we've gone back to the form of the general equation before we started saying CSTR or PFR. So this always applies. So we just go back there, and now we say we've figured out what we need to put in here. So and actually this is a balance written over the whole reactor. So we say now, well, I can't give you a single function for my whole reactor. It's not like the CSTR where I could just use log mean temperature difference. In the PFR, I have no idea how that temperature difference is going to vary down the tube. So what I could do instead is try to get this equation in a form that lets me consider at each stage down the volume. So if we just differentiate this equation with respect to volume everywhere, and let's just do this. So if you differentiate this with respect, differentiate this with respect to volume, then of course you'll get dq dv here, so that's there. And then you have to differentiate this. And here that's a constant, these are constants. And the only thing that's not constant is here in the limit. So don't be deceived. This equation doesn't only have constants. It does have a temperature at the end, and that temperature, we regard that as, well, that's a temperature that's varying with volume. So to differentiate a function where the variable is actually in the limit of integration, you can look up the Leibniz rule for differentiation, and you can show that you take the coefficient and you write it, you take dt dv. You can see an extra term arising here, and that comes from the other term, and so we'll talk about where this comes from now. But you've just taken the factor in there, fa naught theta cp, so fa naught theta cp, so this stuff is like a constant, and then you've got t integrated in t. So if you look at this as just t, then you've got basically dt dv, right? So dt dv times this is basically the derivative of this whole thing. So that's where this part of it comes from. Then if you look at the rest here, again you have this t thing, and then you've got x. So both these, this t and this x, they are both varying down the tube. You do have this, and it's given at the reference temperature. Remember, we broke up the heat of reaction into the reference value and the other part. So this is basically a constant with respect to volume. So when we differentiate, this just disappears. It disappears if you differentiate just this factor, but of course when you differentiate here, then you have to retain it. So anyway, you can think of this as a derivative of a product. So you'll get the first term if you keep this as a factor, and then you say dx dv. So you've got a dx dv part here, and then if you keep that constant and you differentiate here, we just said that you'll get a delta cp and then a dt dv. So you just group that delta cp to where you know there's a dt dv part also. So there's your delta cp here, and that's where we kept the fa naught x as a constant. So fa naught x and then delta cp. Right, so that's just from differentiation, and then like we said, you've got that other factor with the dx dv there. So you've got all of this, and now you've got dx dv here. So you've got your material balance. So you can say dx dv is just minus ra over fa naught, and you can substitute that here. And then your dq dv, remember we've got all this here. So dq dv, you can see an integral in v. So dq dv is simply uata minus t. So that's, we just write that in there. And then here we've just substituted the dx dv part. So that's there. Right, so that's everything then. That's our energy balance for the plug flow part. And even though we used dx dv to get rid of one of the terms, we still have x in here. So we do need x as we integrate this. But of course we can get it just by integrating this equation simultaneously with this one. So we solve these two equations together, and that gives us both conversion and temperature as a function of distance down the tube. Right, and here's the example to try that out. So here you are just given a bit more information that you can use in this integration. And if you do that, see that you can get these results. Okay, so that's all I wanted to do today. yeah, we've basically just established the energy balance, and we've applied it to our reactors. Obviously, you can apply similar considerations to your batch reactor, and I do have a nice case study for the batch reactor, which we'll come to. So all of this works. It is how we estimate the influence of temperature on our reactors. There are other aspects to this. We'll talk about some of the limitations. There are cases where you've got an equilibrium limitation in terms of what you can accomplish, and temperature control actually gives us some options in terms of navigating around equilibria. So there are some very nice, interesting things we can do by controlling the temperature in this reactor. So we'll start looking at that next time.